right, welcome. This next talk is about when to not use APIs. I hope you don't hate me for that. And actually, it's also not true. It's all about options and trade-offs. So hello, folks. I'm Dirk. I'm a principal solutions architect. I work at Amazon Web Services. And in my role, I help my customers on their journey into the cloud. I provide guidance on software architecture for cloud workloads, and the discussion is typically all about options and trade-offs. So, and today I would like to tell a little, very tiny story about integration architecture and durable needs that you have when you build software systems. But first, to motivate a little bit the integration aspect of everything, it's basically that every company, no matter what segment or what industry, has to deal with integration scenario on every layer, basically. And one that makes it quite tangible, I know it's a little bit beaten, but is, of course, when you used to have a monolithic application and cut it down into a set of standalone systems, independent systems. I don't want to stress the term microservices too much here, but this is an obvious case where you have to deal with integration scenarios a lot. So we can learn a little bit from the nature in that context, and we can enjoy my nice vacation photos here. So as an architect, you would see a monolith here and some potential for legacy reduction. And look at that. We can learn from Mother Nature. She also carves out the first component out of this monolith, and this is what companies typically do when they find that their monolithic application becomes unmaintainable. Deployments take ages and always fail and all the like. Or you want to grab a class out of your code base and you have the entire spaghetti ball in your hand and cannot get it out of that spaghetti bowl anymore. So in reality, after a while, companies would typically end up in such scenarios where you have a lot of systems that you need to integrate with each other. But even if you don't cut down a monolithic application and build a landscape of microservices, you will always have systems that need to be integrated with each other. And some of them might have to work together closer. They are physically located closer to each other. Some of them may be a little bit far away. For instance, SaaS solutions or so that you need to integrate with. In any case, what we can learn from all this is that integration architecture is nothing that you just leave aside and look after that if you have 5 minutes or so. It's a fundamental aspect of your modern application architecture. So, integration scenarios. Unfortunately, there's a whole lot of ways technologically wise, how to integrate two systems with each other. And that is all the pain of the ambiguity. You need to understand the trade-offs for each of those approaches. Today, I would like to focus on these two, APIs, since this is an API conference, and messaging. Other than that, there are also other aspects that you need to take into account when you, no matter what concrete technology you use, but then there are also the other aspects that you see here. And this is also something that can be quite painful to understand with your specific workloads. And all of these approaches come with different trade-offs. And sometimes companies say, yes, but we want to have that one approach and that one technology that just solves everything for us without any pain. And this, unfortunately, does not exist. So whatever architecture decision you take, there's always something that sucks, and you cannot do anything about it. You just need to be able to identify the option that sucks less than all the other ones. And touching on the durable needs, that I have mentioned in the beginning. A few examples for those, probably you can relate to them. So if you want to build software systems, what you would probably want to increase is the flexibility for an evolution of your systems and the end customer experience. What you probably want to decrease is the number of lines of code, because the best line of code is the one that does not exist, and operational responsibilities. All right, with that motivational introduction, let's look at the entire thing from the perspective of distributed systems, and with the introduction of a number of systems that you need to integrate with each other. Actually, that's the good context here. Four of the main aspects of distributed systems you can see on that slide. And unfortunately, we cannot touch on all of those in the time that we have today, but we will focus on the first two ones. And I want to make it a little bit more tangible with providing made up but yet realistic example use cases and architectures. And also the customer is made up, but it is a quite nice one. We call it Wild Rides. It's our most favorite technology startup, and it replaces old guard taxi cabs with unicorns, because it's a lot more fun to ride on a unicorn than in a taxi cab. And they have a modern architecture with a microservices landscape. Of course, they run in the cloud, and they are all serverless. But let's see what they have today. And let's start with the first aspect of distributed systems, which is coupling. And coupling is actually the magic word of distributed systems. And it basically means the more two systems are coupled with each other, the more it becomes difficult to change one of them independently. It has many dimensions. We can see a list here, which is probably not even complete. And let's start with the very first one, the temporal dependency. And the example use case for that is ride booking. So let's assume we have a Wild Rides customer. They have a mobile app. They type in what they want to do. So from where to where do they want to ride and when? And this request goes from the end user app to the backend, and it hits the ride booking service first. Now, what happens next? Under the hood, there are a number of downstream systems that all need to be involved and orchestrated by the ride booking service. Wild Rides uses the synchronous request response pattern. So they have HTTP-based APIs, and all of those downstream systems receive the requests from the upstream systems. They take a while, and there's even a third-party payment service provider involved here. And eventually, the end user receives their result. We have learned yesterday, I stole this slide with a screenshot from Bill, that REST APIs are still the most used API style. So that's great. And Wild Rides also uses that. And we've learned from Jim yesterday about certain ways how to build terrible APIs for people you hate. And there is probably one person out there that hates most of the APIs that call themselves RESTful, which is Roy Fielding, because most of those APIs actually are not hypertext driven. But of course, for Wild Rides, that is the case. So what can we observe now here? If the system, particularly if the system is under load, we can see certain request paths that are followed here. And since this is all synchronous, we block resources along those request paths. And the observation that Wild Rides have here is that when a downstream service hits a limit, then they don't only have to scale out the downstream service, but also the upstream services. Because due to the nature of the synchronous communication, we block resources along that request path. And so what we can do here is to change the approach from synchronous request response to asynchronous request response. The first thing that Wild Rides now are going to do is to improve the user experience a little bit. And when they send the request to the ride booking service, it immediately responds with a notification, okay, dear customer, we have accepted your booking, we are now working on it, but rest assured we have all the necessary data for that. So the customer doesn't need to look at that spinning wheel all the time. And you want to return something like a task or a status object that the client can also ask for an update, but of course you also want if you're done, eventually you want to use a push notification so that nobody is forced to poll all the time. And now they do the same under the hood. Send asynchronous requests. HTTP luckily supports that. Everything responds with 202, accepted. That goes also to the next layer downstream, with the only exception that the third-party payment service provider is not able to support this. They still only support HTTP-based synchronous APIs, nothing else. Are we missing something here? Does anyone think something is missing so far? Well, we are missing the responses at least, right? So, and there's a simple explanation. This would overload the diagram, but rest assured, eventually, when the processing in the downstream systems is done, the responses will be sent back to the right booking service or the next upstream service. But aren't we still missing something? Well, yes, we are. I mean, those downstream services need to know where to send the responses, right? They should need to get that information. And what else is missing is that the right booking service or any upstream service needs to have a mechanism to assign an incoming response to a request that was sent out previously. So for that, we attach some meta information in each request. And the patterns that do this is correlation ID, which is a unique ID that you put into your downstream request, and the downstream system needs to inject it again into the response that goes upstream. And you also add a return address. So a URL, for instance, that tells the downstream system where to send the response. So with that done, our example customer now experience that even under load, the amount of scale-out activities have much reduced, and they can scale every system now individually. That brings us to this conclusion: friends don't let friends rely on synchronous integration. Next thing, the availability dependency. Let's go back to the previous version of this example architecture. The thing with two parties that want to communicate over an API is that they both need to be online, otherwise it will hardly work. But then you can also run into problems, right? Let's say in this example, the right payment service runs into trouble. Maybe it is overwhelmed. Maybe it needs to be taken offline for planned or unplanned maintenance. What can we do now? Okay, and this is where messaging can come into play and help us really a lot. So the difference between communication via APIs and via messaging is that you have that, with messaging, you have that message channel that decouples both communication parties from each other. So it's an additional component, and both sides actually don't need to know anything about each other anymore. And one of the manifestations of a message channel is a queue. And the semantics of a queue is that whoever is on the right-hand side of that queue, each of those processes that competes for messages gets one message, and every message is consumed only once. And another cool thing is, and this is important for us now, that queues can buffer messages. In that respect, you can actually consider a queue also as a buffering load balancer. This is one of the durable needs that wild rides have. They need a resilient architecture, and particularly when it's about unknown scaling requirements. Coming back to the previous version of our architecture, let me simplify it a little bit and only use the first level of downstream systems here. Otherwise, the diagram would be a bit too overloaded. We can now just replace the API requests with queues. And what we are obviously doing here is offloading the operational responsibility to the messaging infrastructure. So I would, of course, propose to not operate a messaging system on your own, because that really requires a lot of skills and a lot of staff, but would use a serverless managed service in the cloud. And you probably have your cloud service provider of choice, and I believe they should have such a service here. Now we can also complete the picture and have a look at the response path again. So in each of those response messages, you will see the correlation ID that has been submitted by the ride booking service initially. And with that, we have reduced the availability dependence between the communication partners. The ride booking service is still able to send out the requests downstream, and the downstream systems can catch up in case they are offline or run into congestion at their own pace. Another aspect of coupling is the location and the semantic dependency. So one durable need that wild rides have is that they just want to add components into their production workloads that can also take part in the communication that is going on. We've looked at queues so far, but there's another manifestation of message channels which are topics. And this is also known as publish, subscribe, or fan out. So in this case, every consumer on the right-hand side, it's called subscriber now, will receive every message. We can now replace the queues here with a topic. And what we can do with that is that we really abstract from the location dependency. So the ride booking service also didn't have to know about the location of the downstream services before with queues, but it becomes really more clear now when you work with fan out, with topics, that you can address an unknown amount of downstream services without even having to know where they are, what they are, and so on. And another nice aspect is the semantic dependency that you can get rid of. So probably previously you would have sent individual requests to the unicorn management service, to the ride payment service that all looked a little bit differently. Now you can send just one and the same request to every downstream service. And to not spoil with the availability independence that we put up previously, we can also combine topics and queues with each other and get the best of both worlds. So, and with that, we would end up with this architecture. Now, just for the sake of completeness, there's another approach for pub/sub messaging or fan-out messaging, which is message buses. And the use of this is a little bit more broader, like for an entire application, while topics are typically used for use cases or micro use cases. Right, now let's also have a quick look at control flow and flow control. So depending on what technology you use, you actually have a different control flow. The data flow remains the same between A and B, but the control flow is a little bit different. And this is something you also need to understand. But what I actually want to share with you is the capability of queues to shape traffic. And if we look at our previous use case again, let's think about that the marketing team of Wild Rides runs a massive campaign with a call to action, book your ride for next week, for instance, now already. And that can lead to a massive spike in our backend. So let's have a quick look under the hood, what can happen here. So first of all, within the ride booking service, we can decouple different parts from each other. You would probably want to have something like a managed API gateway that accepts those requests first. And then you can add a queue inside of the ride booking service that, that protects the pre-processing resource actually from that spike of loads. And it's not only about that you maybe cannot scale out fast enough, but maybe you also want to limit the amount of compute resources that you need to pay for in the end. We remain with the new booking arrive topic that also to the right-hand side shares messages with downstream systems, but we also listen to it internally. And then we have the type of compute that actually does the booking processing, and we can protect it again with a queue that flattens the peak load for us. As always, as I mentioned before, all of that goodness also comes with a trade-off that you need to pay for. And in this case, you need to be aware of the flow control. In such a case that you have a fast producer, which means probably through this massive marketing campaign, if you don't spin up enough consumers on the right-hand side, you might run into a time-to-live issue with your messages. So this is something you should always have on your mind. Takeaway from that one is that queues decouple control flow, but require flow control. Which brings us back to the statement from the very beginning, that every architecture you take comes with a trade-off, and it's important to understand those trade-offs. And this is where I'm going to stop today. Thanks a lot for listening. Please reach out to me if you want to discuss this more. And other than that, thank you. Have a great day. Bye-bye.